Hey guys, welcome to Budding Genius Academy. As always, my name is Amelia Williams. I'm a second year mathematics and statistics student at the University of Toronto, and I'm really excited to teach you guys something new about derivatives. Now, this is the third in a three-part series about derivatives that we've been exploring over the past couple weeks. This video is going to be talking more about derivative laws and how we know that these laws are true. Now, in this video, I want to warn you that we are going to be discussing some limit laws within this video that we haven't touched on in other videos. Now, without going into limits too much, we want to make sure that we are able to really fully understand everything that's happening in this video, but you can't really learn about derivatives without learning about limits. We didn't touch on limits too much in this series because otherwise the series would be way too long. So if you're in the need of a bit of a refresher, perhaps go back, look at some online resources. There's some great ones for limit laws and just sort of refreshing your mind about what those are, or just introducing them to you briefly if you've never discussed them before. I will try to discuss as well as I can without completely derailing the video why these limit laws are true and what they mean, but that's just a little bit of a warning for everybody hopping in. But other than that, I hope you guys have a really enjoyable time. I hope you find something that you really like to learn about this and you get a fuller understanding about derivatives and why we use them. So let's hop into it. All right, so one of the first sort of rules about derivatives that we're going to talk about is the addition of a set of functions and the derivative of that addition. So when I talk about a set of functions, I mean something like this example that I have here, where we have one function here in this x squared and another function in this x. So if f of x equaled x squared and g of x equals x, then this would be given as f of x plus g of x. Now these two are incompatible. We cannot add them together. So this is the most simplified form of this f of x and g of x. And so this is what makes this the addition of two distinct functions. Now, in past videos, we've talked about various ways to find the derivative of this sort of all-in together function. So let's say that this whole thing maybe equals h of x, which is equal to that f of x plus g of x. We've talked about how to find that derivative of h of x, and we can go through a couple of sort of quick ways that we did it. So in the past, we found patterns in specific functions with just one term, like just this or just this, and we could maybe come up with a guess that we have as to what this whole thing would equal. And we've also used the idea of a limit to determine this whole derivative. So let's go through using that limit just as a refresher and see how we would find it. So from the limit definition of a derivative, we found that the derivative of f of x, or f prime at x is the way I like to put it, equals the limit as h approaches 0 of f of x plus h minus f at x all over h. Now, using that formula, we're going to plug in this given function and calculate it out. So this derivative equals the limit as h approaches 0 of x plus h squared plus x plus h, that's that first f at x plus h, minus x squared plus x all over h, which we can simplify. So we have that limit sign. We can simplify this, factor out that x plus h squared, and this becomes x squared plus 2xh plus h squared plus x plus h minus x squared, and distribute that minus sign, minus x all over h. And then we see that we have some terms in common, so this is in common with this is in common with this, and now what we have left is equal to the limit as h approaches 0 of 2xh plus h squared plus h. That's what we have. These are the terms left, this one, and this one, all over h. And they all have an h in that, so we can factor out the h's. So this is equal to the limit as h approaches 0 of h times 2x plus h plus 1 all over h. These two cancel each other out, and then this is just the limit as h approaches 0 of 2x plus h plus 1. And as h gets closer and closer to 0, this whole thing will get closer and closer to just equaling 2x plus 1. So there we have it. The derivative of this function right here is equal to 2x plus 1. Now, this is a very long and complicated process to get an answer, and it would be great if we could find some sort of way to just know instinctively what the answer to this derivative would be. So, let's see if we can sort of use the same method, but come up with a rule that works for just any general addition of f of x and g of x. So, if we keep the same sort of idea going forward, that we want to apply the limit definition to this function, so that this equals the limit as h approaches 0 of f at x plus h. I'm not going to have enough room. Hang on. Plus g at x plus h, that's the first term, minus f at x plus g of x, all over h. Then we get that this equals the limit, if we just rearrange this, because it's all simply addition or subtraction, so we can rearrange them within and it'll equal the same thing. F at x plus h minus f at x plus g at x plus h, and then distribute that minus sign in, minus g at x, all over h. And we know that from previous sort of younger grade knowledge of fractions that a plus b over c is the same as saying a over c plus b over c. So we can split up these fractions, apply the limit to all of them. The limit as h approaches 0 of f at x plus h minus f at x all over h plus, because there's a plus sign there, g at x plus h minus g at x all over h. Now, here comes the first of our limit laws, so get ready. I will write this one in red so that you know it's a limit law here. So, we have a limit law that says that the limit as h approaches 0 of some thing, some function, so in this case let's call it a of x plus b of x, is the same as saying the limit as h approaches 0, or as x approaches some number a, call it x approaches a, of a of x plus the limit as x approaches a of b of x. So basically what this is saying is that the limit of two functions, the limit of the addition of two functions is the same as saying the addition of those two limits, which is a little bit confusing, but you can basically break it up and apply the limit to both halves of the addition evenly. So that's what we're going to do here. Because we have sort of one function here and a second function here, we can break it up and apply the limit evenly to both sides. So we have then that the limit as h approaches 0 of f of x plus h minus f of x all over h plus the limit as h approaches 0 of g of x plus h minus g of x all over h. And these two are equivalent statements. That's what this limit law in red says. And now we can finish it off by saying, well, this looks mighty familiar, and so does this. We know these to just equal the derivatives of f of x and the derivative of g of x. So, after all that, the important information is, when you have the addition of two functions, trying to find the derivative of that is the same as saying the addition of the two derivatives. And this makes sense with what we've calculated. Let's consider what our previous example said. We said that d over dx, or the derivative of x squared plus x, equals 2x plus 1. And that's what this whole system that we wrote earlier proved. But if we break this up, and we say d over dx of x squared and d over dx of x, and the addition of those two, which is what this law is saying, we can split up and find the derivatives of both of those. This becomes x squared, you take the power down and add it as a coefficient, and then subtract the power by 1, so it becomes 2x. That's what we proved in a previous video. And here, this is x to the 1, so the derivative would come down and it just becomes 1 as the coefficient multiplied by the power subtracted by 1, so it would be x to the 0 or just 1, so that just is 1 times 1 or 1. And we add them together, so then this whole thing yields 2x plus 1. So instead of having to do all of this sort of long limit proof, we can just say that when we have a function that is the addition of two smaller functions, the derivative of that original function is the addition of the derivatives of the smaller functions within. And we know how to do those almost instantly because of the patterns that we proved in a previous video. So with all of that in mind, it makes calculating things like this function right here, or if these two numbers were different, a lot faster than doing it with a full limit method. So we can say that the addition of two functions, finding the derivative is the same as finding the derivative of each part of that function and adding them all together. And that's what we've proven here for any general f of x and g of x. All right, that's awesome. Okay, so now let's move on to the next idea that we have here. All right, so multiplication by a constant. Well, as before in a previous video, we did talk about this derivative, and based off of the patterns in the video that we found previously, we sort of can have a guess of what we think this number is going to be. But let's go ahead and use the method that we know works to prove exactly what we're 100% sure is the derivative of this, and that method is the limit method. So we can say that this derivative applying that limit method to it, right? We apply that just basic f of x plus h. In this case, we just add an h to every x. So we have 2x plus h squared minus 2x squared all over h. Not too hard. Now let's simplify. So we can factor out that x plus h squared, and it becomes x squared plus 2xh plus h squared minus 2x squared. Oops. All over h. Which now we can apply the 2 to. So distribute that 2 in, 2x squared plus 4xh plus 2h squared minus 2x squared all over h. We have two terms in common, so we can have them cancel each other out. That's a really bad h there. So then the limit as h approaches 0 of 4xh plus 2h squared all over h. We can factor an h because there's one in every term. So h times 4x plus 2h over h. These two cancel each other out as well because there's one in the numerator, one in the denominator. Oh, running out of space. So this equals the limit as h approaches 0 of 4x plus 2h, and as h gets closer and closer to 0, then this 4x will be added to a number that gets closer and closer to 0. So when h is basically 0, we can say that this just equals 4x. So we have that this derivative of 2x squared equals 4x. Okay, so again, as we did before, that's an effective way to get the concrete answer that we believe to be the derivative, but there must be a quicker way to do that, particularly because this is just a single term and we have so many rules and so many patterns that we calculated for single term derivatives. So let's apply that exact same method that we talked about earlier to this whole statement and see if we can find a way to calculate the derivative of a function with a constant being multiplied to it as quickly as we can. And when I say a constant, that's what this sort of number is here. This stylized r represents the real numbers. And so this means that c belongs to the real number. So it is a number. It isn't equal to some other multiple. It doesn't have an x in it. It doesn't have anything that would be considered a function. It's just one concrete real number. So with that in mind, here, I'll move this. Just keeping that in mind, we can start. Here, this is all a little bit smushed. I'll just sort of draw a line here. There, whatever, good enough. We can calculate away at this derivative given just any number multiplied to a function, any function. So the first thing that we can do is apply that limit definition the same way that we've been doing always, because we know that this works. We know that this is a good way to find the derivative of anything. So we're applying that limit definition. So we say cf at x plus h minus cf at x all over h. Now this term c is in both halves of the equation, so we can factor it out of the numerator. So we can say the limit as h approaches 0 of c times f at x plus h minus f at x over h. And as we know from other discussions that we've had about fractions, a times b over c is the same as saying a times b over c. So we can take that c out of the fraction. So c times f at x plus h minus f at x over h. And now here's where we apply another limit law. So I'm going to do it in red as well, just so that you know. Here's another limit law. The limit as x approaches a, or as anything approaches anything, of c times a function, a something, so in this case let's call it h of x, is the same as saying c times that limit as x approaches a of h of x, where c belongs to that set of real numbers, or c is just a number. So that is another limit law that seems to be fairly applicable here, because what it's saying is that when you have a function being multiplied by a constant and a limit is being applied to that whole thing, you can factor out that c from that limit with no issue. So you can take this sort of constant that's here and just move it outside of the limit. So let's apply that idea, because we have a limit here and we have a constant here, so we can move that constant out of the limit. So moving that constant out of the limit, we get c times the limit as h approaches 0 of f at x plus h minus f at x over h. And now that looks very familiar, right? That's just equal to c times the derivative of f of x. So what we're saying here then is that the derivative of a function that's being multiplied by some constant is equal to that constant multiplied to the derivative of that function. So you can move that constant outside of the derivative, perform the derivative on just that existing x, and then multiply those two things back together and get the same answer. And that makes sense to what we saw here, right? Because if we're considering this d over dx, or this derivative of 2x squared, we don't know instinctively how to solve 2x squared, but using the patterns that we found in the previous video, we know how to find x squared, the derivative of that, really easily. So we can say that then, if we separate out that 2, and we hold it, and then we try to just find that derivative of x squared, well, we know what that is. We have that 2 separate. We bring that power down as the coefficient and then subtract the power by 1, right? So it just becomes 2x, and 2 times 2 times x is equal to 4x. So these two things are equivalent ways of proving the same thing, but this side is a lot faster and a lot quicker to do, and we can almost just do that in our head. So this is a really, really effective way to be able to calculate derivatives of functions that are being multiplied by a constant super easily. We can always just move that constant out and find the derivative of the function itself. And there we go, that's what we've proven here using this limit law. Alright, so that's awesome. So we have our addition of derivatives, we have multiplication of a derivative by a constant, And now let's move on to something that is a little bit trickier, a product rule for derivatives. So looking at this, we have two functions, f of x and g of x, that are being multiplied together. Now, intuitively, we don't necessarily know how to solve this. Sometimes it's easy if we can multiply f of x and g of x together to get one long function and then find the derivative of that using rules that we already have. But consider if f of x was maybe sine of x and g of x was x cubed. Those two things cannot be multiplied together. They're not compatible. So in that case, we need a way to be able to calculate the product rule of two functions that aren't compatible to be multiplied into one function. So let's consider two functions f of x and g of x. Now, we're going to do the same thing that we've done in every other time we've started to do something that had just basic functions, or anytime we've tried to find the derivative of something that we don't have an existing rule for. We just apply that limit law because it's a really effective way to find the derivative of anything. So let's apply that limit, let's figure it out, we'll get through it and we will see. So applying that limit law, we have the limit as h approaches 0. I'm going to do this in a smaller pen because this is going to get really messy in a sec. The limit as h approaches 0 of f at x plus h times g at x plus h minus f at x times g of x. In that first half, wherever there's an x, we substitute it with x plus h, and then the second half is just the same as the original function that we're working with. All over h. Okay. So there's not all that much we can do here. There aren't terms in common that we can mess around with. There's nothing that we can really do. But one thing that we can do is if we have, a plus b, and we introduce another term, and so we call it a plus c minus c plus b, these two things are equal because as long as we have plus c minus c or plus something minus something, those two things just net out to equal 0. So it's the same thing as saying a plus 0 plus b or a plus b. So with that idea in mind, we're going to add and subtract something into this equation to make this whole thing be able to be rearranged a little bit more. But it's perfectly legal because it seems as though we're just adding 0 to it. It doesn't change it at all. So what we're going to add is, we still have that limit sign, is h plus 0. So we have that f of x plus h, g of x plus h, and then we can add to this, or we'll start with the subtraction, negative f of x times g at x plus h. And if we subtracted it, we have to add it as well. Oh, this whole thing is going to go off of the page here. Let me move it around. So negative f of x times g of x plus h plus f at x times g at x plus h minus that second half, f at x, g of x. Alright, so that's a little bit messy, but we haven't done anything to change this. We've just subtracted a term here and then added it back here, so it's the same as saying we just added 0 to this equation. And of course, we say it's all over h. Okay, so now we have a lot of stuff going on up here, and we have terms in common that we can factor out. So from the first two, we see here, we have this g at x plus h in common, so we can factor those out. And we end up with g at x plus h, and what's left is f at x plus h minus f at x. And then in these second two terms, we have that f of x in common, so we can factor those out. And we have f at x, and what's left is g at x plus h minus g at x. All over h. Okay. Well, now we're going to apply that limit law that we applied in the first video, where if you have Now we're going to apply that idea that we did in the first video, where if you have a plus b over c, then this just equals a over c plus b over c. We're going to split this fraction. So we're going to have this equal the limit as h approaches 0 of g at x plus h f at x plus h minus f at x all over h plus f of x g of x plus h minus g of x all over h as well. And then now we can apply the rule that we talked about in the first video, this one here, where the limit of two functions that are getting added together is the same as the limit of each individual function added together. So we can apply the limit to both sides of this and split these into two limits. So this is the limit as h approaches 0 of g at x plus h times f of x plus h minus f of x over h plus the limit as h approaches 0 of f at x times g at x plus h minus g of x all over h. Okay, and now we can rearrange this, because this term here, this limit of g of x plus h, as h is getting closer and closer to 0, it's not going to have any bearing on this except for it to equal a real number. So this becomes a real number, so it becomes sort of a number, and in the same case here, this f of x is always just going to be a real number at x. So these can be sort of considered like those c values that we had previously. So we can use this limit law that we had here, where when c is a real number, we can take it out of the limit. So since g of x plus h is a real number when h is closer to 0, or under the circumstances where it does equal a real number, we haven't talked about continuous functions where the limit may not be real, but considering in most cases where g of x is just a real number, we can take that out. So we can say that g of x, whatever number that is, take that out using that other limit law that we talked about, this one here, as a constant, times the limit as h approaches 0 of f at x plus h minus f of x over h, plus, same case here, f of x is always going to be a real number at x, so we can take it out. F of x times the limit as h approaches 0 of g at x plus h minus g at x over h. And now this and this, I'll do this in a different color, This and this certainly look familiar. So we can simplify them to what we know and say that then this is equal to g of x times d over dx of f of x, or the derivative of f of x plus f of x times d over dx, or the derivative of g of x. And there we have it. So that is our rule that we have, where d over dx of two functions, or the derivative of two functions that are being multiplied together, is the same thing as saying the second function times the derivative of the first plus the first function times the derivative of the second function. And this makes it a little bit more simple for us, particularly if that f of x and g of x have very simple derivatives that we can calculate really easily. So with that law in mind here, that's now our rule. We can go through some examples really quickly. So the first example that we have here is this f of x equals x plus 1, x minus x plus 2. So with that in mind, using that law, let's say d over dx, or just f prime at x, whichever, equals that second term. We're going to make this f at x and this g at x. So the second term, x plus 2 times the derivative of the first, and let's think about it. Now we have the derivative of x plus 1. Well, it's two functions that aren't compatible. We can't add them together to make one term, and we've already proven that the derivative of two added functions is the addition of each of their derivatives. So it's the derivative of x first. X to the 1 just becomes 1. And that power goes down to 0, so it gets multiplied by 1. So then the derivative of x is just 1. And the derivative of 1 is, consider that 1 times x to the 0. So that 0 comes down. It gets multiplied by 0 times x to the negative 1. Anything times 0 is 0. So it's 1 times 1 plus 0, or just 1. So there we go. That derivative of f of x is just equal to 1 plus plus the second term, plus the first term, right? Plus f of x, x plus 1, times the derivative of g of x. And so the derivative of g of x is very similar to what we talked about before, right? D over dx of x plus 2. Again, it's just equal to the derivative of each of the terms because it's an addition, and we've already proven that the derivative of the addition of two functions is equal to the addition of each of their respective derivatives. So the derivative of x, we've already said, is 1. The derivative of 2 is the same as the derivative of 1, right? It's 2 times x to the 0. Move that 0 down. Anything times 0 is 0, so it's 1 plus 0, which also equals 1. So then this becomes times 1. Then it's just simple algebra. 2 plus x times 1 is just 2 plus x. X plus 2. And x plus 1 times 1 is just x plus 1. And we can add these together. X plus x is just 2x. 2 plus 1 is 3. So then the derivative that we have all in of x plus 1 times x plus 2 is 2x plus 3. And there you go. So that is one way to solve it. Now, of course, with this, there is another way to solve this. And this is always something that you should check before you embark on using this rule that we've proven on this x plus 1, x plus 2. We can say that these two are compatible. We can multiply these and simplify this to be an easier statement. So we can do that, right? It's the FOIL, first, outside, inside, last. That's that multiplication that we have to do. So with that in mind, it's x times x is x squared. Outside is x times 2, which is 2x. Inside is 1 times x, or x. And last is 1 times 2, or 2. So then this is x squared plus x, 2x plus x is 3x plus 2. And then the derivative of x squared plus 3x plus 2, well, it's the addition of functions. So we can use that same rule that we've used for the addition of functions. Finding the derivative of that is the derivative of each of the respective ones. So this becomes d over dx of x squared plus d over dx of 3x plus d over dx of 2, using that rule that we proved at the very beginning. And we can use our patterns that we've already talked about. X squared, bring that 2 down, and the power gets subtracted by 1, so it just becomes 2x. 3x, well, the power is 1, bringing that 1 down, multiplying it by 3 doesn't do anything. But in this case, we also have that 3 is a coefficient, which we talked about earlier, meaning that we can take that coefficient of 3 out, right? And then this becomes just 3 times d over dx of x, just to make everything a little bit more confusing, right? Plus the derivative of 2 we already said was 0. And then 2x plus 3 times d over dx of x. X has a power of 1, bring that 1 down, multiply it by x to 0 is just 1. So the derivative of x is just 1. So this whole thing is 2x plus 3. See, two equivalent ways to calculate the same thing. Now this one seems to be a little bit longer because you do all those sort of break it up step by step. But if it makes more sense to you, both of these are totally cool ways of being able to calculate out the multiplication of two functions. But as I said at the beginning, sometimes you have two functions that are not able to be multiplied together. If you had, a sinusoidal function as well as an algebraic one, then those two would not be able to be multiplied together, and then that way you would definitely have to use this first rule that we talked about. But either one of these are okay, so long as these two are able to be multiplied together. All right. So, on to our very last one. This is the quotient rule for derivatives. So we proved when we have the derivative of two functions being multiplied together. Now we want to try to prove when we have the derivative of two functions being divided. So we're going to consider trying to find the derivative of h of x, but we're going to make this a little bit more into something that we've already seen. So at the end, what we're trying to find is this h of x, which is equal to one function divided by another function. So f of x divided by g of x. But first, we're going to rearrange this equation a little bit so that we see something that we have that we've seen before. So if we have this h of x, we can say that because we know this, we also know then, therefore, if we were to rearrange this function a little bit, we could say that f of x is equal to, if we multiply g of x to both sides, h of x times g of x. These two things mean the same thing, right? This is just one way to rearrange this whole thing. If we multiply g of x to both sides here, then we get this second equation here. So with that in mind, we're going to apply the product rule that we've already talked about, because the product rule means that if we have h of x as one of the products, somewhere within that, we're going to yield that derivative of h of x that we've been looking for. Now for this question, I'm going to use the notation that this means the derivative of f of x, because we're going to use a lot of derivatives here, and it's going to get really hard to write that d over dx every single time. But just so you know, that means the derivative of d over of f of x. They both mean the derivative. Okay. So we're going to apply the knowledge that we have. So if f of x equals h g of x times h of x, which it does, then we're going to say then that we know, based off of the rule that we proved earlier, that the derivative of f of x is equal to that derivative of the first times the second plus the first times the derivative of the second. And I rearranged them slightly so that g of x is always first, but it's the exact same as the rule that we proved up here. This one. So, I maybe flipped some of the multiplication signs around, but either way, you know that this is true. Okay, so in here, we can see that we have this h of x that we want. So let's find a way to isolate that h prime at x so that we have exactly what we want. Okay, so we can move this term over, so we have f prime at x minus g prime at x times h at x. So we move this first term over to the other side, equals g at x times h prime at x. And now we can divide both sides by g of x and have that be the denominator, and then we've isolated that h prime at x. I'm going to flip over the equal sign just so that we always have that h prime at x on the left hand side instead of having it on the right hand side, but it'll mean the same thing. So h prime at x is equal to f prime at x minus g prime of x times h of x, all divided by g of x. Okay, now we've isolated that h prime of x. Alright, so we're happy with that. But what we don't love in here is the fact that we still have that h of x, because when we're finding the derivative, having the original in the statement isn't super helpful, because it just makes the whole thing a little bit muddied, particularly if we haven't been given an h of x, we've just been given f of x over g of x, right? If we wanted to calculate just this, we don't have that h of x, and trying to find that whole, trying to figure that out so that we put those in doesn't really make all that much sense. So we're going to substitute in that original definition that we have for h of x though, which is that it equals f of x over g of x. So let's do that. So h prime at x is equal to f at the derivative of f of x minus the derivative of g of x times f of x over g of x all over g of x. Now, this whole thing is getting a little bit gross, but we can rearrange this so it's f prime at x minus g prime at x times f at x over g of x, like that. So we can extend that g of x. Now again, this whole thing is still over g of x, and then we can extend it even further. We can apply it to that f prime at x, but if we're going to add it to the denominator, then we need to add it to the numerator as well, so that it doesn't become an incorrect statement. So we have f prime at x g of x minus g prime at x f of x over g of x, that's that numerator, and then as well still over g of x. And when it's divided by the same thing and then divided by that again, we can restate that as saying it's being divided by that thing squared. So f of x the derivative of f of x times g of x minus the derivative of g of x times f of x over g of x squared. And so there we go. We can't simplify it anymore. We have here, let me move this down a little bit just so that we can finish writing this. We have a final statement, and we can say concretely then that we can even substitute in that original definition, and we can eliminate the h of x altogether. We can say that the derivative, let's do it in a finer pen, the derivative of f of x over g of x is equal to the derivative of f of x times g of x minus the derivative of g of x times f of x over g of x squared. And there we go. There is our quotient rule for derivatives. And we use that we found that with the product rule that we found in a previous question. We just rearranged that product rule until we found something that worked for us when we have an f of x over a g of x. And then to round out this video, let's just do a real quick example of that so you can see it in action. So we have this, let's call this x squared is f of x, and g of x is x squared plus 1, because it's just the numerator and the denominator. So let's go through these quickly. So this equals, that first one is the derivative of f of x, which is x squared, times g of x minus the derivative of g of x times f of x all over g of x squared. Alright, now we won't necessarily go in and solve this whole thing because it'll be really long, but we can go through, we'll do the derivatives, and then you can see that it's just algebra after that. So the derivative of x squared is, bring that 2 down, decrease the power by 1, and it just becomes 2x times x squared plus 1 minus the derivative of x squared plus 1. Well, it's the derivative of two functions, which means that it's the derivative of each of those individual things. So we can split those into two derivatives, and we can say that then it becomes Derivative of x squared, we already said, is 2x. And the derivative of 1 is 0. So it would be just 2x plus 0 times x squared all over x squared plus 1 squared. So if we make the top 2x cubed plus 2x minus 2x cubed, right? Because this is just 2x times 2x squared over 2x squared is x to the 4 plus 2x squared plus 1. We can subtract those. This becomes 2x over x to the 4 plus 2x squared plus 1. And there we go. That is the derivative. Now that's not necessarily intuitive just looking at it. It isn't as nice as if, say, the derivatives were just the derivative of the top divided by the derivative of the bottom. But it is a rule that helps us get there a lot faster than it would if we had to do that whole thing with the limit definition. So there we go. So we've got a whole bunch of new rules here. We got 1, 2, here's another one here. They're all in stars. We got a whole bunch of new rules that we can apply whenever we're calculating the derivatives of different things. This one I did in red, but I had to do it in blue. So with all of these new rules, we can apply these to different combinations of derivatives that we have. So if we have f of x times a g of x, if we have f of x plus g of x, or f of x over g of x, all of these things, we know now how to calculate the derivative of multiple levels of functions, including that make up one big function. All right, so that's a lot of information that you got sort of thrown at you today, but I hope you guys understood most of what we're saying. I have a little bit of a quiz for you guys just to make sure that it's all sort of cemented in your brains. These are various find the derivatives of different combinations. So this one is obviously an addition. This one is multiplication by a constant. These are the product of two functions, and this is the quotient of two functions. So you can use all of the rules that we talked about in the videos today. You can screenshot this, print it out, write it, or just think about it in your head, whatever you want to do. But if you have answers for all of the questions and you think that they're pretty solid, you can send us an email at this email address down here, buddinggenius@buddinggeniuscm.com, and submit sort of the answers that you got and say, I think I got all the answers right, and you can get 20% off of our summer camps if there's any left by the time you're watching this, or our tutoring services. And I hope you enjoyed this video. I hope you learned something new. I hope you found something that you liked, or just a refresher about how we come about finding the rules that we do when it comes to derivatives. And I was really glad to be able to teach you guys something new today. So I hope you have a wonderful day, and I'll see you in the next video. Bye!